This is Brian Putt. Today I want to talk about evaluating complex value of information problems with SIPmath. This resolves a couple of different issues. One is it's very easy to have multiple indicators with many uncertainties that generate a tree that's way too large for traditional decision trees. In other cases, you may need to have total transparency of the decision policy. And when the decision follows several indicator nodes, it could be very complex and difficult to decipher out of a decision tree. And what I'm going to talk about today solves both of those issues. So let's consider a conceptual tree where we have 4 indicator nodes, indicator 1, 2, 3, and 4, some sort of decision policy, and actually I'm going to assume there's 5 decision policies, one of which is not to develop and the other 4 are to develop different ways, okay? And then following that decision policy, you have 4 reality nodes that correspond to the indicator nodes, and then a well cost, and then there might be some other uncertainties such as price or facility costs, things of that nature. In any case, there are 81 possible different decision policies. And this tree generates 100,000 branches, including only the well cost uncertainty. So imagine if you had facility costs and you had operating costs. Now I'm multiplying that by 10. Now I'm at, 1,000,000 branches. How can we solve this kind of problem, this kind of VOI problem? Well, let's look at it this way. It's going to be 3 steps. The first is to determine the consolidated Bayesian inverted matrix based on the information nodes. So let's assume that we've generated 4 reality indicator matrices, and let's assume they're just 3 by 3 for simplicity, okay? They don't have to be 3 by 3, they could be something else, but let's assume 3 by 3. They don't even have to be, symmetrical. They could be 3 by 2, for example, or something of that nature. What we're going to do is generate a list of the reality codes. So if you look at all the combinations of realities of these 4 things, there's 3 to the 4th, or 81 different combinations. Then we're going to use multiple experiments in the SIPmath, and we're going to simulate 20,000 times. The reason I simulated 20,000 times is because some of the probabilities get really small, the combinations get really small. And I want to make sure there was adequate opportunity for all the combinations to be realized. And what we'll do is we'll record the indicator node, which will be recorded as a 1, 2, or 3 for each of the 4 indicators. And this will be captured in the PM table along with the reality code. Once we've done that, then we're going to count each combination of reality and indicator code into a matrix that's 81 by 81, because we've got 81 reality codes and 81 indicator codes. We can then calculate the joint probabilities, and from that we can calculate the probability of reality code given the indicator code. This is really the consolidated Bayesian matrix based on the original inputs. And it might be well to point out that these indicator nodes could be correlated or anything, and this process would still work, okay? In the second step, what we're going to do is we're going to take that Bayesian inverted matrix and calculate the decision policy. For each of the indicator codes, what we're going to do is sample from reality based on the Bayesian inversion matrix. We'll calculate the NPV based on the full model to include the well cost uncertainty as anything else you might have. And we'll calculate the NPV, or whatever value measure you have, for each of the decision policies. And these will all be captured in the PM table. After this multiple experiment, and I've only used 1,000 simulations here because actually I'm running 1,000 simulations and I'm running it 405 times because I have 81 different indicator codes and I have 5 decisions. That's 405. So after I've run this experiment, multiple experiments, I'm now going to identify the optimal decision policy from these results for each of the indicator codes. All right, we're now ready to go on to step 3. In step 3, we're going to record that decision policy from the previous model into our model. And then we're going to sample from reality, sample from the indicator. That indicator is going to generate an indicator code that tells us what decision policy to use. We then use that in our model, and we incorporate the other certainties here, and that then can be used to calculate the results into a cube-prob graphs. And that's basically it. So one of the things you might do following that is to consider having multiple decision policies that reflect no information, perfect information, and other types of imperfect information. The decision policy for perfect information could be determined by changing the underlying conditional probability decision tree and following the same process. The information value is determined by fixing the decision policy and trying each of the policies separately. There's no optionality in the no information case. So having those two to compare to your imperfect information, I think can be valuable in telling the story to your decision maker. So what are the advantages of this process? We can calculate the conditional probabilities for very complex VOI situations where we have a reality and an indicator. We can handle any level of conditional probabilities. We can consider correlation between those realities. And we can consider multiple decisions. We can also include any number of uncertainties, as we're not limited by the number of branches in the tree. In this example, we had about 98,000 branches. If other types of costs were included, facility costs, prices, this could be multiples higher. While requiring 3 steps, calculating the Bayes, calculating the decision policy, and putting it back in the model, the time required to calculate the results might be much less than running a tree. The same model can be used, but utilized in 3 different ways to determine the optimal decision policy and the results. So there's not a whole lot of different programming. You just need to understand what you're trying to do in each of the steps. If you want more information about this process, you can review some other valuable information videos on the Brian Putt YouTube channel. You can contact me at brian@theputts.com. And if you're interested in the SIPmath toolbar, go to www.probabilitymanagement.org, and you can find the free SIPmath toolbar. However, in this example, I've used the enterprise version of the SIPmath toolbar that allows multiple experiments. Thank you.